Hello, everybody from Seattle, Washington. I am up here for the week, kind of visiting customers, also hanging out with some community members and taking care of some personal business. Um, this is episode number 106. And in this episode, we are going to explore Mike doing a live migration to Cilium in AWS. So it should be a really educational episode. I hope you like it. As always, I am Maui Lion everywhere. So if you want to drop me a note or let me know if you think this is useful, definitely let me know in there. Let's see what else we got. So our news this week. Let's take a look at the eBPF Summit. I was actually just earlier today on a dry run for eBPF Summit. So that's actually coming up real darn soon, September 13th at 8:30 a.m. Pacific, and it will run all the way till 1 p.m. Pacific. I'm really looking forward to the day. It should be really a lot of fun. We have a ton of folks scheduled. We have Brendan Gregg going to be talking about Fast by Friday, leveraging eBPF to improve the speed of software. We have a live presentation by Jane Yang, Vision for eBPF Everywhere. Then we have one of my favorite events every year, which is the eBPF Summit. That should be an absolute blast. I'm really looking forward to that one. And then we have a bunch of other talks that are going to be really great. You know, folks like I'm talking about GPU profiling with BPF at Meta, a ton of other great content. Definitely come and check us out. Check it out. It's a virtual event. It's free to register. Definitely come and register and be a part of it. We also have our newsletter. So what's happening in the newsletter this week? Let's take a look. As always, if you want to sign up for the newsletter, this is how you would go about it. You could just go to Cilium.io newsletter, drop your email address in there. If you wanted to see what the most recent one is, this one came out on 5th September, and you can take a look at what content is. We have getting acquainted with BPF as a security tool. There are a few sharp corners, but capabilities it provides are quite impressive. It can really gather a lot of metadata about what's happening at that layer. In the ecosystem, we dropped a new blog that says it covers the top 20 Cilium use cases, the magic of eBPF, the Qualitative Compass podcast with Liz Rice. Just did another podcast, should be really great. And then Cilium by using eBPF with Raymond DeJong from Isovalent, IT Talks podcast about the project, demystifying eBPF tracing, episode number 9, Beekeeper, see why Red Hat is developing BPFD for eBPF program lifecycle management, sprinkling your eBPF into your observability, just tons of really great content. One of the ones that came out recently that I was really stoked about is this eBPF cheat sheet, this Cilium bubble cheat sheet. I found that to be just incredibly useful. It breaks down all the commands and arguments to Hubble so that when you're leveraging Hubble to understand what's happening inside of your infrastructure, it really makes it a lot easier to understand. I think I might turn this into my desktop background at some point, but it's really, really pretty neat. I really like how that was put together. As always, if you're attending this event, go ahead and drop something in the comments to let me know that you're here. Always happy to know that folks are listening or attending. And let's go ahead and get into it. So I'll come back over to the content. And I've written up quite a bit. So this is actually probably one of the more fully fleshed out notes that you've ever seen me do. Again, as always, if you want to actually take a look at this note or you want to review this note after the event, you can just go to the hackmd/@eBPF. And then right with that link right down there at the bottom right-hand side, it says show notes. You go right to that link and you will see episode 106 in the list, and you'll be able to actually access that note directly. Make sure that it is. Yeah, read by everybody. So you should be able to get to HTTPS hackmd/echo-live/106, and that would take you right to this note. All right, jumping into it. So the goal of the goal of this today is going to be doing a live migration of an AWS EKS cluster to Cilium, and we're going to use a migration method that I refer to as the node pool migration method. Before we get into it, I just wanted to kind of give like a high-level overview of some of the challenges around around doing this work. So at a high level overview, the CNI layer is a very low level component in operating a Kubernetes cluster. And most CNI implementations take care of things like managing IPAM or IPAM address management, as well as the lifecycle of network namespaces and interfaces associated with pods. A good number of them also support network policy to some extent. These different aspects mean that any migration to another CNI should consider each of these elements to ensure that that migration is successful. We often hear from folks that they would prefer a hitless migration, and that all pods during the migration need to allow connectivity during the period of migration. It's okay to restart pods on a scheduled and managed basis, but it's not okay to restart all pods on all nodes all at once. And when considering any migration and any other changes regarding CNI implementations, it's important to ensure that you have a well-defined and tested strategy for the migration. This includes all of the necessary steps to perform the migration according to your migration strategy, as well as how to pause, roll back, and test each step along the way. And this is a considerable effort to get right. It should require testing and determine success and failure metrics throughout the process. All right. Then I want to get into like some of the Cilium migration tooling, because there's actually tooling that Cilium does. So has as part of its solution. So during the install, so when Cilium is installed by default, Cilium would override the existing CNI cluster itself, right? The existing CNI configuration in a cluster itself. And it does this by placing the file in etcni netd 05 Cilium complex on the underlying host and the necessary Cilium CNI binary in op CNI bin. It can be configured not to do that. And so there are some flags in Cilium to actually support, like where do you want to put that file? What do you want that, what do you want that file to be called? Do you want to not lay down a file at all? Do you want to manage that with some other mechanism? Then we have the operator, which is the next step in our journey. And it is actually a pretty important one because the operator does some pretty interesting stuff as it relates to managing Kubernetes environments. One of the things it does is it has a feature that allows us to watch for pods that are operating but not managed by Cilium. And when it does that, it will determine that those pods are not managed, and it will restart them so that Cilium can grant them an IP address and that pod can then move under the management of Cilium. This is a destructive process. And in the particular case of migration that I'm going to be exploring today, I'm going to be migrating from one node pool to another node pool. And that means that I will have pods on both node pools that are active that should not be restarted by the Cilium operator until the migration is all the way complete, right? So it's an important thing to be aware of, and it can be configured, right? So you have the option of setting the unmanaged pod watcher. By default, it's set to true, and it will look every 15 seconds for pods that are not managed. You can also set restart to false, and it will not restart any pods until you come back through and change that home setting post migration. So another thing that Cilium can do is IP address management. And by default, Cilium will actually use a mode called IPAM mode cluster pool. And what that means is that it's not actually going to look at the pod sliders allocated to the nodes by default. It's just going to allocate a new pod slider for every node using the cluster pool IPv4 slider list, which by default is 10/8. This can obviously be configured. There's tons of options here to allow for Cilium to manage IPAM correctly according to the environment in which you're going to be operating. And the cluster that I'm going to be working on now, the cluster has been brought up leveraging the AWS CNI. And in AWS CNI, we call that in the Cilium terms, we call that ENI mode. That means that Cilium has the ability to manage all of the pods and IP addresses just like the AWS CNI does. It can be a direct replacement for each other. And when that happens, you have to configure Cilium to be in that new configuration mode. But here are some of the parameters that you can use to configure IPAM mode if you want to go a different route, including this option here, where it's the mode option. And if you want to read more about those mode options, there are quite a few. You can actually go and look at this concepts IPAM document, and that will take you there. So just go ahead and look at that. So these are different modes for IPAM. Including things like Kubernetes host scope mode, Azure IPAM, and AWS CNI mode, and Google Kubernetes mode. So each of these different areas actually provide for different configuration associated with Cilium's configuration. In this context, we're actually describing that you can actually set the IPAM to equal ENI. You can set that mode to ENI, and we will actually manage Cilium's ENI interfaces, allocate them to pods, just the same way that AWS CNI does. There's also some options to provide a custom ENI configuration if you want to. So there's tons of capability here. Configuring Cilium with the subnet tags filter. ENI allocation parameters, what type of instance type, etc., etc. IPAM min allocation, IPAM max allocation. This is a pretty neat feature that we do with the Cilium side, where we actually pre-allocate IPAM for our ENI nodes, ENI interfaces, so that you're not waiting for the ENI to be allocated to the node before associating that ENI with a given pod. Tons of capability in the ENI mode that we're not going to really explore too much today because we're just going to be exploring migration. But suffice to say, there's tons of capability here to actually manage this. All right, so let's keep moving. We also have a relatively new feature as of 1.13, and you've heard me talk about this before, which is per node config. And this means that you can provide an overlay of configuration that you would like to have applied to nodes based on a label associated with that node. So if you're in a Cilium cluster and you do Cilium config view, you'll be able to see the global set of values that are configuring all Cilium nodes. But if you then also look at the per node config, you'll be able to see that we can override or adjust particular settings based on labels associated with nodes. This gives us the ability to do perhaps like an in-place migration, where we would, and if you watch the previous eCHO episodes, I covered that pretty well in detail. So per node config is a pretty good tool for managing the specific configuration of specific nodes based on labels. Migration strategies. Depending on the environment and the existing CNI implementation, there are a number of general strategies for handling a CNI migration, and each of them has its advantages. So first, let's talk about the constraints. There are a number of constraints to consider when evaluating a migration strategy. In some cases, it's possible to spin up a new cluster with the new CNI and migrate pods to the new cluster. When considering stateful pods, this can be challenging. Now, there are tools like Valero that can take a backup of a set of resources, including their state, and restore them to a different cluster. But you can see how this would still incur some downtime and require that the state be copied correctly from one cluster to another. These tools can be useful in migrating pods where you have the time to take the pod down and bring it up on new infrastructure. So the big constraint that we face a lot of the times is this downtime constraint, which refers to a state where pods will become unreachable during a period of migration. At a high level, downtime is a normal part of the lifecycle of pods in Kubernetes environment. When changing the underlying CNI, these pods need to be restarted so that it can be configured to use the new CNI. Then we have connectivity. Connectivity between pods on different CNI implementations is a complex topic. So for example, in our scenario where we're bringing up an AWS cluster, we'll have some nodes managed by the AWS CNI. We'll have some nodes managed by the Cilium CNI. Can pods in both of those two node pools still reach each other? That's an interesting topic, and it can be very complex depending on the different types of scenarios that you're working on, right? So if all pod IP addresses are routed to nodes, as is the case in KubeNet, in AWS, in AKS, or in EKS for that matter, then we can use Cilium to replace the function of managing the pod networks on each node and rely on the existing routing mechanisms to outside the node to ensure that traffic continues to flow. In scenarios where we're changing the type of encapsulation, perhaps migrating from a direct routed scenario to an overlay configuration, this can be a bit more difficult. Specifically, we need some mechanisms to ensure that routes exist on all nodes to be sure that traffic can be routed during the period of migration. And finally, and this is an important point, finally, network policy. Different implementations of a CNI implement network policy differently, right? So in Cilium, obviously, we implement this in eBPF, but in Calico and some of the other tools, perhaps you implement this in IP tables. If we're in a scenario where we're trying to allow for pods to communicate and we have two different forms of network policy applied to the same node, that can really create quite a lot of confusing scenario, quite a lot of perhaps unexpected challenges in allowing for this, especially if you're going to introduce a new IP address allocation that would be perhaps a new CNI. So there's lots of things to consider about like how you're going to be numbering these particular pods, how you're going to be handling the migration of them, et cetera, et cetera. The first one, there are a couple of different ways to handle this. One of them is in place, where you actually have the existing CNI deployed. You're going to deploy Cilium, and you're going to go on a node-by-node basis and replace the underlying CNI implementation and not bring up any new nodes, just like replace the CNI implementation on that node. That will incur probably a reboot, at least one reboot for every node in the process. And it can be done, but it definitely has its advantages and disadvantages and complexities to it. The next part is node pool migration, where we're going to leave the nodes that are configured by the current CNI alone. We're going to bring up a whole new node pool, and we're going to configure Cilium on the new CNI on that new node pool. And then because these are basically two node pools under the same Kubernetes cluster, we're going to migrate work from one side to the other until all things are moved. And then we're going to scale down the old node pool and destroy it. And that's actually the mechanism that we're going to be using today to kind of show this live migration in AWS. For validating connectivity and testing, we're going to use a tool like Goldpinger to actually do this work. And Goldpinger is a tool that on startup will actually do a discovery of all of the other Goldpinger pods based on a label query. And then it will establish connectivity between them and then give you a pretty handy UI to be able to see what that looks like. So our first goal here is to bring up an AWS cluster using the existing AWS CNI, and we're going to actually bring up two different node groups. We're going to call it node group 1, which is the default one. That'll be the existing one managed and serviced by AWS CNI. And then we're going to bring up node group Cilium, and that will be the new ones that will be serviced by Cilium. Now, to do this, I've actually already I've created this EKS configuration to show you kind of like what that would look like. And so in this EKS configuration, this is a configuration file for bringing up an EKS cluster. I've gone ahead and created DC Migrate in the US West 1 region. And under that, I've actually created two managed node groups just to keep my life simple. The first one is NG1. I'm going to be using instant type M5-.large. I want 3 of these nodes running, and I'm going to set the volume size to 80 gig. This is leveraging private networking. And then I'm also going to create another node group. And in this other node group, this is going to be the one where we deploy Cilium. I'm going to use the same size. I'm going to use the same, but in this case, I'm not going to actually create any nodes. I'm just setting this to 0 because we're going to scale it up as part of our work here. But I'm also passing an argument into the configuration that allows me to taint the nodes, node Cilium.io, agent not ready. This is a taint that the Cilium agent knows how to manage. So once the pod comes up, once Cilium is operational on that node, then it will remove this taint. Now, there was something to talk about here. This is the bit here. So this taint, it has an interesting effect. This taint the effect is no execute. And when you actually mark a taint on a node of no execute, that can actually also trigger an evacuation of that node, because effectively that's an action that the node controller will take action on. That means that if the node itself were to become were to come up and have that no execute taint on it, then it would try to evict any pods that were running on that node, and that may cause problems in your infrastructure depending on how you handle that. There's another effect that you could use, which is no schedule. And no schedule only takes effect on scheduling rather than on execution. So using no schedule would actually be safer. In fact, I'm going to go ahead and change that because that would probably be a better recommendation. But I wanted to talk through that so that you all understood what we were looking at here. So we'll go ahead and put that in here. And we actually have written up quite a bit on helping understand why this is necessary. So the taint no schedule means that, when the scheduler is making its decisions about what nodes to schedule work to, if the node itself is tainted no schedule, then that means that we won't consider that node for scheduling new work. And that moves the onus to the scheduler instead of to the actual node controller on the node itself, making the decision about whether to execute pods or, in fact, evacuate them. So let's go ahead and create this cluster. I have already done this because I wanted to, in the interest of time, as it were. So I have kubectl, get node, in theory. I see what happens. Okay, so AWS Vault, exec, Cilium demo, and kubectl, get node. There we go, that's better. I use a tool called AWS Vault to manage my AWS credentials. I cannot recommend it enough. It's a very cool tool. Let's take a look at that real quick. Up by 99 design. This tool, it's such a cool tool because it allows you to actually securely manage your configuration. So like the keys that I use, the access key and the secret key, that's actually not in clear text on my disk. It's hosted inside of my GNOME keyring or inside of my K-Wallet keyring. And then when I use AWS Vault Exec, it's actually going to generate a token, a one-time credential. It's going to create temporary credentials using Amazon's STS service to allow me to log in. And then those things can be rotated. I can exit, go back in, etc. It's really, really cool. Very secure way of handling those credentials. I'm a huge fan of it. Here we are. We got our cluster. All the pods running. We got kubeproxy running. We've got Coordinates operating. We have AWS nodes up and running. The first thing I'm going to do is I'm going to go ahead and deploy a sample application. So I'll go ahead and deploy this guy. And I'm going to edit the service. Type load balancer because we have that capability in an AWS cluster. So let's go ahead and use that. And we'll do watch. Curl. Refresh, but it will eventually resolve because we are going to be using an ELB for this. So as soon as that all propagates across the distributed system that it's DNS, then we should start seeing results here. In the meantime, let's go ahead and split horizontally. AWS Vault Exec. And then we'll go back to our instructions here. So got our sample application deployed. Let's go ahead and see if our service has propagated. Hey, it has. Cool. So here we are, we're looking at our service here, and the way that I have this deployed is in two different ways. I have a deployment with the actual pods running, and then I also have a daemon set, and that's why you can see the two different name types. Like you have a name that has a Goldfinger and then dash and then a little hash, and then you have Goldfinger deployment hash and the little hash, and that's two different things, right? So if I look at those things deployed on the command line, Kernel, get pod. I see all of those pods. If I do Kernel get vs deploy, you can see we have a daemon set of Goldfinger with 3 running. We have a deployment of Goldfinger with 5 running. And they're all on the existing nodes in the existing cluster. No changes have been made. It's the standard EKS cluster running all the things. Okay. So for our next trick, I'm going to go ahead and close a bunch of these windows that are not relevant to our discussion. I've gone ahead and deployed the sample application. I've validated connectivity. Things are talking. That's what the gray lines are for. And we see the green dots for everything communicating. The next thing we're going to do is we're going to go ahead and reconfigure the AWS node daemon set. Now, to do that, before we do that, let's talk about what that is and why that's necessary. So the AWS node daemon set is the thing that's laying the AWS CNI down on all of the nodes. And it's a daemon set. And that means that as new nodes are created, whether in the same node pool or in a new node pool, that the AWS node pod will run on that new node. And when it does, it will lay down the AWS CNI. We have an intention that we want to actually stop the AWS CNI from being laid down on new nodes. We want to label existing nodes, telling us what CNI is actually operating. And then we want to actually limit the daemon set to only those nodes that exist right now. And that way, as we spin up new nodes in the new daemon set, we can ensure that the AWS node CNI will not deploy there. So let's take a look at how that would work. So first thing I'm going to do is I'm going to label all nodes CNI equals AWS CNI. I do a kubectl get nodes -l CNI. All of those are labeled. All of those are labeled. If I look for nodes that are not labeled this, I should see none. Right? All of the nodes are labeled correctly. Next, we're going to modify the AWS daemon set to only target nodes with the AWS CNI node label. So this is what the node affinity looks like for the AWS CNI right now. And what we want to do is we want to actually add a new key and value pair to the affinity statement, saying that it has to also match key CNI operator in AWS CNI. Let's jump over here and do that. So here's that node affinity statement for that bit. And the rest of these affinity statements are actually pretty interesting. But what I want to do is add a new one. So I'll do key. Let's paste. I have it already put over. Yeah. Okay, so I'm going to go ahead and line that back up in my YAML. So this is, so let's look at the ones that are here. So first we're saying for this pod to be scheduled on a node, then the key Kubernetes IO, the label Kubernetes IO/OS has to include the term Linux. And the architecture has to include either AMD 64 or ARM 64. And the EKS Amazon compute type cannot be not in Fargate. And then lastly, we're going to add ours, which is key CNI, the label CNI, operator in AWS CNI. I'm going to go ahead and apply this. And what that's going to do is it will cause the AWS CNI to restart on those nodes. They're also ready. You can see that, 11, 16, 20 seconds. So these have all just restarted. Shouldn't have had any impact on our connectivity, but let's go look. For our gold pinger status, everything's still connected. And now, as we add new nodes, the new nodes will not get the AWS CNI nodes unless they're labeled accordingly. All right, once that's done, the next thing we're going to do is we're just going to go ahead and validate connectivity, which we've already done. And the next thing we're going to do is we're going to scale up the node group for Cilium. And we're going to test our logic to see if that new node label or that new affinity rule will apply correctly. So we're going to use EKS. So we're going to scale the node group for the cluster DC migrate. The name of the node group that we want to scale is ng Cilium. We're going to set it to nodes 3, and we're going to set the nodes max to 3. And let's see what we see. We should start seeing the new nodes come online here. I'm going to be right back, grab something to drink while we're waiting for these new nodes to come up. There we go. Here they come. Got some new nodes showing up here. Clean up my screen. Now we see new nodes, and we can see things like we can do that same label thing that we did before, right? Let's take a look at the nodes that are not labeled CNI, AWS CNI. And we can see that they're in a not ready state. And that's because these nodes do not yet have a CNI deployed. So they're going to be in a not ready state because there's no CNI deployed. And if I look at CNI with AWS CNI, we can see that that's there. If I do kubectl get pods, you can see that all of these nodes are present. All of these existing pods are present. And because these new nodes are not in a not ready state, the daemon set itself has not actually deployed there yet. Now, earlier in my process, I did actually have a problem where I had set the daemon set with a toleration. And this is worth mentioning as well, right? So if I do yes, Goldfinger. So down here, I don't think there are any tolerations on here at the moment. Yeah, it looks like no, there are not. But there is a toleration that you can apply to a configuration. And that toleration can be pretty high risk because because the toleration is toleration operator exists. And when you do that toleration, that means that any taint that you apply will be ignored. And it's an interesting point because if you do that, what that'll mean is that, you know, if you have operator exists as a toleration, it will totally ignore every taint and try its hardest to schedule there. So interesting point, and it can actually increase the complexity of a problem of a solution like this. All right, let's keep moving. So now we've got our new nodes. We can see that they're not ready. Let's go ahead and install Cilium there. So in the values below, I've configured Cilium to deploy in ENI mode. And that means that Cilium will handle ENIs allocated to a node and configure pods accordingly. We've also disabled the unmanaged pod watcher. We talked about that earlier. If we leave that up, it will restart pods when we don't want them to be restarted. Finally, we have configured affinity for Cilium to only install on nodes that don't match the AWS CNI label. Ideally, we want only nodes that we did not know about before scaling up to NG Cilium node group to have Cilium installed on them. So let's take a look at this configuration. This configuration is set to, we have a few ENI specific settings. We have egress masquerade interfaces, E0, ENI enable true, eBPF post legacy routing true, and PAM mode ENI. That's where the IPAM piece comes in, right? That's handling the ENI mode for IPAM. We have our operator configuration, disabling the unmanaged pod watcher. The service accounts we're going to create. We have tunnel disabled because we're in EKS. We're going to enable Hubble. We're going to enable Hubble relay. And then we also added in some affinity statements. And in that node affinity, we're saying the label CNI cannot include the value AWS CNI. So it's like a negative match. All right, so let's go ahead and take a shot at what that looks like. So I'm actually going to use Helm to do this install because the Cilium CNI does have an option to restart the pods directly as well, and I don't want that. So I'm going to use Helm to do this install. Let's take a look at what that would look like. Here's our Cilium values again. They all look correct. We'll do Helm install Cilium -n. Cilium. We'll go for 114.0. Values. Cilium values. Now, you'll note that the affinity I defined was only for the agents. I did not define an affinity for Hubble. I did not define an affinity for Hubble relay. I didn't define that affinity for the operator. So these things could deploy in a variety of different places, and that's fine, because eventually we will actually have them all on the Cilium nodes. But just be aware of that because we didn't configure it. It is configurable. I could put the affinity for this up into each of those locations as well, but I did not do that by default. Okay, now let's take a look at you see Cilium operator running. We see Cilium coming up in nodes. So now those new nodes just became available. That means a kube proxy propagated across all 6 nodes. Goldfinger's daemon set just propagated across all 6 nodes. But if you look at the nodes themselves, we see that we only have 3 AWS node pods and we only have 3 Cilium pods. So that means that we're in pretty good shape here. Let's go and take a look at whether we have connectivity between all the things. Do a refresh. Hey, look at that. So this means that pods that are on the existing AWS nodes are still able to talk to pods that are on the Cilium nodes. Right? We have full connectivity between all the things at this point. Okay. So exciting. What happened there? Other connectivity? I can still see myself. Let's see. Oh, I must have typoed it or something. All right. So we still have all of our connectivity still working. Everything's there and everything's working. So at this point, what we've got is we're in this hybrid state, right? We have half of our cluster operating on Cilium, half of our cluster operating on AWS CNI. So that means that if I come back over here on this side and I do kubectl get Cilium endpoints, you'll notice that I only have the 3 Goldfinger nodes and the 3 Goldfinger pods that have actually been allocated to my 3 new nodes. I don't have any record of a Cilium endpoint for any of the rest of this work. I don't have any of the Goldfinger deployments. I don't have any of that stuff over here yet. The only thing I know about from Cilium's data plane perspective are just these 3, which are allocated to those new nodes. So that's pretty cool. But at this point, now we've got Cilium deployed. We've got, we can actually see, if we wanted to, we can actually see which Goldfingers are on our side. We can see Cilium endpoints. We can prove connectivity still works. The next thing we could do is we could record in the nodes that have CNI, AWS CNI. Let's go ahead and do that. And that will make those 3 nodes unschedulable. Take them out of the scheduling algorithm for those things. It'll get pod or get nodes, sorry. We can see scheduling disabled, scheduling disabled, scheduling disabled. Right? But just to make sure that's the right one, get those -L CNI equals AWS CNI. The ones that match that label are currently scheduling disabled. Now, if I go ahead and restart the Goldfinger deployment, we should see all of those pods get rescheduled to nodes that are considered for scheduling, or the new nodes that created Cilium nodes. Let's go ahead and try that. All of the pods have been rescheduled, and they're all up and running now. And if I do kubectl get CEP, like I did before, I should see all of those new pods show up under the control of Cilium, because they've now been migrated basically from the old node pool to the new node pool. And if I go back to our connectivity test and refresh, I can see that everything is still able to communicate with everything. But if we were to look, but you don't see core DNS here, right? Core DNS is another one of the ones that is part of the overlay network, and it's not currently on my list of things that are managed, right? So how can I determine what nodes are currently managed and what nodes are not managed inside of Cilium? One way to do that is to actually diff the set, right? So look for pods and differ it and do a diff between pods that are managed and unmanaged. And there is eCHO.com. Cilium. Is something in the hack? No. I believe it is in here under the contrib. Probably in the contrib. There we go. So there's a tool called khunmanaged.sh. And what this is going to do is it'll give us a list of those pods that are not currently managed by Cilium in a way that we can actually use in a useful way. So let's go ahead, let's throw this into a script. And what it's going to do in the first function is going to get all the Cilium endpoints that we know about. The second function is going to get all of the pods in the cluster with some filters, right? And then we're going to actually skip the ones with host networking enabled or in the pending and not in a running or pending state. And then we're going to sort all of them and then we're going to unique them. So let's take a look. The ones that are not managed by us right now are those two core DNS pods and also the 3 Goldfinger pods as part of that daemon set. So those are the ones that are currently unmanaged in our cluster. So the first thing we'll do is, well, let's go ahead and migrate this one over, right? So we can do kubectl rollout restart -n system limited core DNS. And now I can see the core DNS has moved over. And now it looks to me like we don't really have anything left not managed. These 3 daemon set nodes, but I can't really do anything. I can't migrate those because it's a daemon set, right? It'll just put one agent on every node that is in a ready state. So these I can't migrate. I'm going to abandon them. They're a part of a daemon set that I can't really change. All right. So we've done the work of handling the migration case. We've moved everything over to the new case. We moved everything over to the new configuration. Everything in the cluster is working. We're able to group connectivity. The next thing we're going to do is we're going to scale down the existing node group. We're going to remove it from use. So we'll do eCHO scale node group. One that we're going to scale is ng1 for the cluster PC migrate. Some nodes are actually nodes equals 0. And when I do that, it's going to start shutting down the old nodes because all of our work is now on the Cilium side. So, node 0. Okay. Now, if I do watch, get nodes, you should start seeing those old ones go away. while we're waiting for that to happen, I'm going to do one more thing. Because we're actually going to get rid of we don't want the AWS CNI to, start adding itself to new nodes as they get created, etc. What we're going to do next here is we're going to go ahead and do kubectl delete ds-n kube system. Sorry. That's all. That demo. Kubectl delete. Yeah. That's node. And I'm doing that because I'm just going to remove the risk of that showing up on new nodes, right? I don't want it to ever show up on new nodes. So I'm going to actually just remove that AWS node daemon set completely. And we will start shutting down those old nodes and they will start getting deleted. There we go. Our old node group is going away. Goodbye, old node group. It's been a pleasure. Now we only have the new node group with Cilium deployed. And we can scale it up. Scale node group. And if we watch for a little while longer, we're going to see those new nodes come up. We should see Cilium get applied to them. Doesn't take too long for this part to work. There we go. New nodes coming up. We do kubectl get pod -n kube system watch. See the new Cilium nodes showing up on the new nodes. Kube system is already running there. In fact, our kube proxy is already running there. Up and happy. You can see kubectl get pods. You can see a bunch more daemon set pods running. Just scale this up, scale deployment, go here. Let's make it 100. Woo! Oh. 50. How far we can scale. Not sure actually how far that'll go, but there's a limit to the number of ENIs per node, but woo! That's really cool. So you can see it actually propagating now. And we have like basically a full mesh across all of these things. Totally insane. All of these agents. It's such a pretty graphic. I love it. Don't see any red lines though, which is neat. Okay. Now, just for kicks, this is also pretty wild. We can do Cilium, bubble, port forward, bubble, So bubble all of those we know about. Then we go all connected, and then we can do bubble status, bubble observe. We'll just watch it. That's all of the traffic moving back and forth between all of these agents, just spamming each other on port 8080. How wild is that? Kind of watching a real-time view of that. Totally insane. Anyway, it's very noisy, but it does a really good job of actually helping us understand whether things are connected and working correctly. Okay. So that, my friends, is the work of doing a live migration of Cilium, or to Cilium, from the AWS CNI. We've learned quite a bit. We've learned a bit about the affinity rules. We learned a bit about how the mechanism works. I've documented all of this. If you want to check out the documentation for this, you could definitely go to our website, as I mentioned before. It's hackandbeta.io/echolive/106 copy. I'm going to go ahead and put this in the chat so that you can see it. And that gives you access to the documents that I've written here. Let me know if you have any comments or questions. Come hang out in Cilium Slack. Definitely come hang out with me at eBPF Summit next week. I hope that you all have the best weekend of your lives, and I will see you next time. So have a great time. Thank you for joining us. And sorry. See you next time.